mode and full particle entanglement. So in this slide, I show you the quantum Fisher matrix for full mode and full particle entanglement, which is given by this matrix. And if we calculate now the sensitivity to the sum of parameters, you discover that this is given by 1 over m squared, where this square is related to mode entanglement, 1 over the average number of particles square, where the square, the number of particles, is related to particle entanglement. And the Heisenberg limit is reached by this state. There are several reach. This is Heisenberg limit for full mode and particle entanglement. So missing slide was the conclusion. So to conclude my talk, I can tell you that parameter estimation, so the bottom line of my talk is that parameter estimation is a very rich and interesting quantum technology. So it's a technology where entanglement plays a key role and also a clear role. So here it's very clear what is the role played by entanglement, k-partite entanglement, and also the interplay of mode and particle entanglement, as we have seen from the multiparameter estimation. It is experimentally relevant. There are many experiments with photons, atoms, ions, and so on. And this figure that I show here is representative of all the experiments with atoms so far. Is related to foundational concepts such as quantum distinguishability, quantum speed, coherence, and so on. So it's a very broad interest. And it also characterized by concepts that can be applied to other tasks, such as quantum simulation. And this is something that I discussed. So this characterization of ground state of many body system, but also to quantum computing and so on. So the good part of my talk was based on this lecture note and this review that is available in the literature. And with this, I would like to thank you very much for your attention. Thank you very much.
Thank you very much, Dr. Petze, for the very insightful talk. And now I would like to ask, does anybody have any questions for Dr. Petze? No? Okay. I actually have a question regarding last part of your talk, you basically start mentioning the multi-parameter estimation. Is this still just some theoretical or are there already experimental data or research already going on in this direction?
Yeah. Okay. Okay, let me, it's a little bit disturbed, the signal. So I repeat the question. So your question is whether there are experimental activity multi-parameter estimation.
Yes.
Okay, yes, there are actually a few experimental results with photons actually. So in the group of Rome, the group of Fabio Sciarrino in Rome, they use the Fock state of single photons split in different mode in order to see the sensitivity. And this is done with integrated photonics. There are, however, other groups that use of my knowledge, no experimental results so far, but of course this is a theory that can be extended to the case of atoms, of course.
Okay, thank you. Another question that I was not very, how to say, I'm not sure if I understood it correctly, but this plot where you were comparing the spin squeezing factor to the quantum Fisher information, and it seems like spin squeezing, so it's basically a subset of the, so quantum Fisher information can measure more area of the,
Yeah, exactly.
does it, I mean, okay, but how do you say, like, is it just because the squeezing parameter itself has a limit of probing this entanglement? So if you want to kind of like really, so is Fisher information basically a best like a better estimation, like a better parameter for probing the usefulness?
Yeah.
Okay.
So the quantum Fisher information is the optimal actual probing of the usefulness of a state for metrology. So there is a necessary and sufficient probing, I would say. So the Fisher, so you can reach substitute noise sensitivity if and only if the Fisher information is larger than the number of particles. So
And
this the problem of yeah. So it gives the full 100% characterization of the state. The spin squeezing is an efficient characterization because it uses variances and mean values of spin observable that can be easily or relatively easily measured experimentally. However, it does not include all the relevant state. Essentially, the problem is that not all the relevant state has a reduced variance. For instance, the JZ state does not have a reduced variance. And the other problem is that this JX that is on the denominator, this can be very, very small for certain state. For instance, for the twin Fock state, the spin squeezing parameter is a 0/0. So it cannot be characterized, the state, with a spin squeezing parameter. Nevertheless, if you calculate the quantum Fisher information, you see that it goes like n²/2 essentially. So the analysis of the quantum Fisher reveals that this state is useful for metrology, and indeed there have been experiments using the twin Fock state that are proved that this state is really useful for metrology.
And a following up question is like, is a quantum Fisher information always accessible from the experimental point of view?
Okay.
Like, yeah.
Okay, so from the theoretical point of view, yes, there is always, for the single parameter case, an optimal observable such that the quantum Fisher information can be measured. The problem is that this optimal observable can be, in principle, very difficult to assess, or simply if we don't know the state, because, for instance, it's a noisy state and so on, we might not know what is the optimal observable. So there are different strategies to assess the Fisher information. So in this slide, I give you an idea of the strategies that have been considered for to get the quantum Fisher information or to bound the Fisher information. So I want to also point out that lower bound to the Fisher information are also very useful because are able to detect entanglement. The spin squeezing is a lower bound to the quantum Fisher, which is experimentally relevant and has been a lot to detect entanglement. Otherwise, people, so in this work by Zoller and collaborator, they have seen that the Fisher information is related to the imaginary part of dynamical susceptibility that can be extracted experimentally. Or we have also seen that is related to the Loschmidt amplitude, so the probability to project the state on itself after a transformation, or is related to the fidelity between experimental histogram that I discussed in the first part. So this fidelity between experimental histograms obtained for different values of the parameter gives access to the Fisher information for the specific measurement, and is a lower bound to the quantum Fisher information that was useful to detect entanglement in the experiment. Then there are several other techniques to lower bound or to assess the Fisher information. But I would say that an efficient detection of the Fisher information is still an open question, also theoretically in the literature.
Okay, I see. And any questions from you guys? I hear nothing. Okay, so I'd like to thank Dr. Pezza again for accepting our invitation, and thank you for giving this very nice talk about some introduction on the parameter estimation. And yeah, I think that's all for our QuSCo on air today. Thank you everybody for attending.
Okay, thank you very much for
the
invitation, and thank you very much for attending the talk.
Thank you, and goodbye everybody.
Bye.